Let's look at one more natural exponential graph, and then we'll talk about properties of natural exponential functions. Looking at e to the minus x. Again, I'm going to make an xy table. And I guess let's use 2, 1, 0, -1, and -2 for x. So first up, when x is 2, I'm computing y equals e to the minus 2. I'll get that from my calculator, and that gives me approximately 0.1. Okay, it's approximately 0.135, blah, 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 but obviously graphing even down to the tenth of a unit accuracy is optimistic for this scale of graph, so that's good enough. What about when x is 1? Then e to the minus x will be, according to my calculator, approximately 0.36, etc. So let's call that 0.4 for the purposes of graphing. If I was just giving a numerical answer, I'd probably carry out more decimal places, but again, there's no point to it when I can't graph any more accurately than that anyway. Okay, anything to the 0 power is a 1. Next, I have y equals e to the minus x when x is -1. That's the same thing as e to the 1, which we said was 2.7 approximately. And last, when x is -2, e to the negative x will be e to the positive 2, which is approximately 7.4. Let's plot those. So I have 2 and 0.1, which is really close to the x-axis. And I have 1, 0.4. That's just about there. I have 0, 1. -1, 2.7. That's more like there. And then we have -2 and 7.4. That's going to be roughly there. Okay. And if we connect the dots, we get the typical exponential graph shape, but going downhill. So what are the properties of natural exponential functions? We're going to be a little more general than just saying y equals e to the x. We're going to allow ourselves to have a coefficient in front of the exponential, and we also want to be able to take into account what if there is a coefficient inside the exponent multiplying the x. By the way, in this model, a sub 0 and k are both positive numbers. Neither one is negative. So that helps us know that if you don't see a minus sign in the exponent, you have a growth function, whereas if you do have a minus sign in the exponent, you have a decay function. In both cases, the domains are all real numbers. In other words, minus infinity to infinity. If you'll recall, that's one of the reasons we didn't want to allow the base to be negative, so that we could use any old x value in the function. The ranges in both cases will be all y values that are greater than 0. In other words, from 0, not including 0, up through infinity. And so what we can say that both of those say about the graph is the domain being all real numbers tells us that the graph extends infinitely far to the left and right. Now you can't always see that on the graph, or it's not always apparent. Like, for example, if we look at, let's say this one, you could almost wonder if there was a vertical asymptote. It almost looks like the graph isn't going to keep going to the right because it's going up so steeply. But in fact, it does. It's just that, to get an x value over here, you'd have to be practically up at the moon to see it on the graph. What does the range tell us? That tells us that the graph lies entirely above the x-axis. Right? There's no negative y values. There's not even a y value of 0. It's all y values above the x-axis. Continuity. Both of these are continuous everywhere. In other words, a little more intuitively, there are no gaps, jumps, or holes in the graph. Now, the y-intercepts in both of these cases are at y equals a sub 0. In other words, at the point 0, comma a sub 0. Because remember, y-intercepts always have the x-coordinate 0, because if you're on the y-axis, your x-coordinate has to be 0. And we saw an example of this up when, this one, where we were graphing f of x equals 2 times e to the x, and we saw that the y-intercept in that case had to be 2. And so that coefficient on the exponential function is going to give you your y-intercept. Let's see, any other properties? Yes, increasing, decreasing. Growth functions, in other words, functions where the exponent does not have a negative sign, so e to the positive number times x, are always increasing. In other words, going uphill as you go from left to right. And decay functions, those are ones where the exponent has a negative sign. And we saw an example of that too, right? Here was one right on this page, e to the negative x. That's a decay function. It's going downhill. And you could think of this as e to the negative 1 times x. So that's a negative coefficient in the exponent. That's going downhill. It's a decay function. And so we say that that is decreasing.